Okay. Generation of energy in a sustainable manner is one of the key tasks in our society. To reach this goal, one has to explore new materials which make energy conversion or energy storage more efficient. The applications where then they can be used are, for instance, in photovoltaics, where light is converted by solar cells into electricity, or in wind turbines, where mechanical energy is converted, or another example would be thermoelectric devices, where a temperature gradient is converted into electricity, and an example for improving energy storage would be improved batteries. The materials which we were aiming at can be rather complex, and this I want to explain in detail on the example of the thermoelectric material. Desired for a highly efficient thermoelectric material is to reach a high figure of merit. The figure of merit is proportional to the square of the Seebeck coefficient and the electrical conductivity, and it is inversely proportional to the thermal conductivity. Thus, one needs a high performance in the electrical properties and at the same time a low thermal conductivity. Promising candidates for such a material are alloys with a complex unit cell. Complex in such a way that the phonons have a tortuous path through the crystal and the thermal conductivity is reduced. And also a complex unit cell can lead to a complex band structure, which then may have multi-values in the conduction band, and this increases the electrical conductivity. As a material, an example for such a complex unit cell is the Clathrate compound. The Clathrate compound of type 1 has a complex unit cell consisting of 54 atoms. It has a host structure forming 8 cages. The host structure is consisting of 46 substitution sites sitting at 3 different Wyckoff sites, the 24K in green, the 16I in blue, and the 6C in red. Inside the 8 cages, one puts guest atoms, which are usually heavy elements, and they should scatter phonons. In our case, we study the Clathrate compound barium, aluminum, silicon. So barium as heavy elements as guests, and in the framework we have silicon atoms, and some of the silicon atoms are substituted by aluminum. Another important feature of the alloy structure is that one can tune the charge carrier concentration, and to count the charge carrier concentration in a simple manner, one can look at the scintille, when one can apply the scintille concept. So for instance, if we consider silicon 46, which is the empty clathrate without substituents, it has no free charges and it is semiconducting. Now we can put the guest atoms inside the crystal in the cages, and for each guest atoms, in the case of barium, we obtain 2 additional free charges, and total 16 free charges, and this compound becomes metallic. These free charges can be compensated one by one by substituting the whole structure with aluminum, and the number of free charge carriers gets reduced. One is expected to find a semiconducting behavior again if one has 16 aluminums inside the crystal, and this is called the charge compensated structure. The main challenge to study the Clathrate compounds is to find the stable structures and determine for each composition, for each aluminum content, where the aluminum sit inside the whole structure. We have a huge configuration space for each composition, and there are some estimates for the number of configurations per aluminum content. This is an upper estimate is given by the binomial coefficient, and the lower estimate is given by the binomial coefficient divided by the number of symmetries of the parent lattice. And one can see for the charge compensated structure we have already over 1 billion possible structures. So we could see this huge configuration and composition space we cannot study by simply using ab initio methods, and high throughput calculations doesn't work either. So our solution is that we use the cluster expansion technique to compute efficiently the energy of each configuration. The cluster expansion technique, as it was already explained in the previous talk, parameterized the energy in terms of clusters, which are a structural pattern. With this cluster expansion technique, once we have the model, we are able to predict the energy for an arbitrary configuration. The cluster expansion technique is not a new technique. There are several packages where this is implemented. These packages usually make a full enumeration of configurations for each composition. And for the clathrates, we saw that there's a combinatorial explosion. And I just want to point out what that means. If you look at our clathrate compounds, suppose we know all the possible configurations for the clathrate. It is already a huge computational task to compute the predicted energy using the cluster expansion model for all configurations at a certain composition without any ab initio calculations. So for instance, at sub 10 aluminum inside the unit cell, we have this computing would take 1 day up to 2 months. Or for the simple charge compensated structure, it would take 10 months up to 30 years. So from these numbers, we can see a full enumeration of possible structures is not an option for clathrates. Now I'm going to show a cluster expansion approach for large parent cell. This cluster expansion approach is implemented in cell, and it has an iterative iterative scheme. This you see here, the workflow, and it has some sampling instead of a full enumeration inside. How the workflow works, I will explain detail on the clathrate compounds, on the clathrate compound. So we want to study the clathrate and the composition range from 6 aluminum to 16. We start for each composition with a random structure and calculate the ab initio energies. This you see here with the black cycles. From this ab initio data set, we construct our cluster expansion model. The predicted energies from this cluster expansion model for the ab initio energies you see here with the black dots. They match well with the ab initio energies, so our cluster expansion model works. With this cluster expansion model, we now search for new lowest non-degenerate structures, so we perform a metropolis sampling in each composition, and these are the gray dots. From this metropolis sampling, as I said, we retain the lowest non-degenerate structures for each composition. These are the green ones. Once we have the predicted lowest non-degenerate structures, we calculate their ab initio energies. In some cases, it matches well with the predictions, for instance, at composition 13. In some other cases, the predictions doesn't match well with the ab initio calculation, for instance, at 6. So our cluster expansion model still have a low predictive power, and we need to improve our cluster expansion model. Because our cross-validation score is large, so we enter into another iteration, the second iteration. So from this ab initio data, we construct a new cluster expansion model. We perform a new metropolis sampling. We search for new lowest non-degenerate structures and calculate the ab initio energies. These are here shown in purple. In some cases, it is found a new stable structure, for instance, at 12, found a new one. In other cases, it doesn't find a new stable structure. This is found already in the first iteration, so it predicts a configuration which is slightly above the ground state configuration. This iterative procedure we continue until we find a good cluster expansion for the full composition range, and we find for each composition the ground state configuration. And we obtain, in the case of the clathrate compound, high predictive power with ab initio accuracy, which is about 1 millieV per atom. And the clusters we use for this cluster expansion are really simple. We only use the 1-point clusters, which are the 3 different WACAF sites, 6C, 24K, and 16I. And we use the nearest neighbor interactions, so the 2-point clusters with sites next to each other, which are here indicated with the colored bonds. So after we obtain this ground state configurations, now we can look at their properties. For instance, we reached a well agreement of the lattice constant with experiment, and we could prove that the lattice constant increases linearly with the aluminum content. Now we look in detail to the configurations. How do they look for each composition? And for this I want to introduce a configuration vector. This here shown here above. Inside the parentheses you have the number of aluminum atoms which go to the K side, or to the I side, or to the C side. And outside the parentheses you have the number of aluminum bonds. So you see in the low substitutional range from 6 up to almost 12, the C side is fully occupied. And with adding aluminum atoms to the structure, the I side gets occupied. This occupation of the I side is a bit contradicting, because if we look at our one-point cluster interactions, the C side is preferred. Then it comes the 24K side. But the 24K side cannot be occupied, since all 24K sides have a 6C side as neighbors. So that was introduce a bond in our structure, but bonds are avoided due to our nearest neighbor interactions. So the bond has to be avoided, and it's energetically preferable to occupy the 16I side. Then in the middle region from 9 to 14, we have a competition of energetically really similar structures. And this I want to explain with an example of composition 9. Here you see 4 different configurations at composition 9, aluminum, and their energy. So the ground state has 0 energy and has the configuration with fully occupation of the 6C side. And the other 3 remaining atoms go to the 16I side. If we now want to save energy by moving 1 aluminum atom from the 16I position to the 24K position, this would induce a bond. So this would raise our energy a lot, so it is far from the ground state by 3.8 MeV per atom. Another possibility is to move out the aluminum atom from the 6C position and put it into a 24K position. That also costs some energy, which is 4.8 MeV per atom, but at the same time we can retain or regain this energy by moving the atoms which sit at the 16I positions to the 24K positions. And then we obtain, by this simultaneous move, a quasi-degenerate state, which is similar in energy to the ground state. This kind of quasi-degenerate states can lead also to quite drastic changes in the structural properties. For instance, if we look at the bond distance, they have a drastic change for the bond distance II and KK. In this plot you see the bond distance versus the aluminum content, and the shaded region shows where these competing energy structures appear. So the ground state has the preferred occupation of the 16I side. Then their ab initio values go here. However, if we now look at the quasi-degenerate state, then which has occupation of the 24K side, then the ab initio values go here, which are quite different to the other values. So it can lead to a drastic change, this quasi-degenerate state. If we increase our aluminum content and reach the charge compensated structure, we have a really well defined ground state, which has half occupation of the 24K side and half occupation of the 6C side, and the remaining atom goes into the I side. And again, no aluminum bonds. So let me stick to the charge compensated structure. There we are expecting to find a charge a semiconducting behavior due to the Sintel concept. Here, this table shows different configuration for the charge compensated structure. And a high energy structure, however, shows metallic behavior, even though it was not expected according to the Sintel concept. If we go to our ground state structure, it has a really well-defined band gap, and it is semiconducting. So we can say we have a strong dependence of the band gap according to the configuration we want to study. And if we want to assign the energy difference from a configuration to the ground state to kinetic energy, we also can express the kinetic energy in some temperature, and this motivates us to study finite temperature effects. So we perform finite temperature simulations to also study the configurational change, what is maybe behind this semiconductor to metal transition. The finite temperature simulations we do is canonical metropolis Monte Carlo simulations at several temperatures. Here you see this simulation for the number of aluminum bonds versus the versus temperature for the charge compensated structure. We see at low temperature there are no aluminum bonds. At high temperature there are many aluminum bonds, and the transition happens around 800 Kelvin. And if you look at the occupation factors of the 3 different Wyckoff sites, we also see a well-ordered state at the low temperature region. As I said, a half occupation of the 6C site and a half occupation of the 24K site. Only a low occupation of the 16I site. The 6C site is always preferred over all other sites. However, in the high temperature region, the 24K site and the 16I site follow then a disordered behavior, and the disordered behavior you can see in this plot with the black line. And this transition also happens around 800 Kelvin. And we can call it, it's a partially ordered disordered transition. Since we observe such a feature for our Clathrate compounds, we are motivated to look at their thermodynamic properties, and we calculated different quantities. Here I want to highlight only one quantity, the specific heat. The specific heat shows a peak at the transition temperature. This plot shows the curvature for 2 different techniques. First, the Monte Carlo simulations, and another simulation method, it's called the Wang-Landau method. And we clearly observe a peak at 800 Kelvin, so we have indeed a transition temperature at 800 Kelvin. So from our thermodynamic analysis, we could confirm that we have a configurational partial order disorder transition at 800 Kelvin, and this drives the semiconductor to metal transition at the charge balance structure. And this, for instance, is the band gap versus temperature, also performed with 2 different kind of methods, and you see that the band gap reaches 0 above 800 Kelvin. With this, I want to conclude. So you could see that we are able to study a large parent cell, and we are able to study with the cluster expansion technique the huge configuration and composition space. This iterative cluster expansion technique is implemented in Cell, and Cell is a part of the analytics toolkit in NOMAD. And you can find our tutorial here. There are several developers involved inside for this package. The creator, Santiago Rigamonti, and also master and PhD students, Martin Kuban and Axel Hübner. And also some people from Fritz Haber Institute as Luca Gringelli and Christopher Sudden. Thank you very much for your attention.